Welcome to our presentation, Scalable Data Platform for Bulk Operations. Hello, I am Anand Kumar, the Engineering Manager for the Data Platform. Our team is officially known as the Transaction Storage Services Group, or in short, TSS. We are part of the Shared Services Organization.
Hi, my name is Hakan Aygün. I am lead engineer at Data Platform team. I am working for Avalara since 2019.
Hello, I'm Sam Grantham. I'm also a lead engineer on the data platform team, and I've also been here since 2019.
Let me start with a brief introduction to the data platform. The data platform provides OLTP capabilities at scale with low latency for a number of Avalara products. It's built on top of a horizontally distributed transactional data store. The data platform, in addition, provides data lifecycle capabilities for compliance needs. It also delivers data at scale to the data lake for further downstream analytical processing by other teams at Avalara. Now that we have covered the data platform introduction, let's turn our attention to the problem background. We started working on this data platform about 3 to 4 years ago. Although the existing system met the demands of the day quite well, we wanted to get ahead of the curve and meet the demands of the future. We first added the OLTP capability to the data platform, along with a phased data migration. We then looked at adding bulk operations capability, which existed on the old platform. These bulk operations are typically triggered internally on a periodic basis by other Avalara services to solve a particular business problem on behalf of the customer. This presentation is about how we added the bulk operations capability on the new data platform, which meant handling hundreds of millions of bulk operations in a matter of hours, on top of already supporting thousands of OLTP transactions per second at extreme low latency. Now that is a tall order. In particular, we'll discuss the initial approach we took, the challenges that arose, how we adapted and overcame the challenges using well-known architecture principles and practices, and last but not the least, the processes we apply to achieve predictable outcomes. I'm going to hand it over to our lead engineers, Hakan and Sam, who built the platform from the ground up to take us through this journey.
Thanks, Anand. Let me start with challenges. Architecting and implementing high-volume, low-latency bulk operations presents a multitude of challenges. One of the key challenges at the architectural level is ensuring data integrity while accommodating diverse workloads, in our case, OLTP and bulk operation activities. Considering that TPS of OLTP traffic can reach several thousands, consuming a substantial portion of our 10K IOPS at the data source level, the most significant performance challenge is conforming OLTP latency SLAs within the boundaries of IOPS limitations, especially under sustained high OLTP traffic. Another major challenge is to create an end-to-end repeatable load testing environment demanding substantial effort and time investment. Identifying bottleneck in particular components during the load test was another challenge. Additionally, replicating issues observed in both individual components and load tests proved challenging and making it harder to find root causes. Given that the solution spans across multiple distinct teams, achieving resolution needs seamless cross-functional coordination. This is the initial architecture of our bulk process. Let me provide some context here. Our team is responsible from the data API, which provides data storage services for the OLTP workload generated by our clients through tax calculation service API. Tax-related data is stored in a sharded main data source, and it is simultaneously funneled into a data lake for utilization by downstream systems. We encounter several issues when the bulk process is added into our architecture. First, Data anomalies emerged due to updates by two different workloads. Second, performance of the bulk operation on the primary data source was quite poor by several factors, a combination of IFS contention and computing resource competition. Also, OLTP latencies began to spike due to the bulk process activities, and it fired alerts for violation of OLTP SLAs. This observation highlighted the need for a comprehensive re-evaluation of our architecture to address these issues effectively. To address challenges and issues, we took a strategic approach. This involved breaking down the problem into separate layers across the integration stack. This method was crucial for making solution scalable, easy to maintain, observable, and testable. Here are the other key elements of our approach. Our solution depends on indirection at data source level. This approach enables us to effectively mitigate the negative impacts of write contention stemming from IFS limitations. We adopted a strategy of simplifying our system architecture. This step aimed to streamline complexities, enhancing both system performance and resilience. Our approach incorporates continual load test iterations. This iterative process allows us to fine-tune the system performance and iron out bottlenecks and ensure optimal performance under varying workloads. Let me summarize of high-level principle to the solution in a nutshell. Architecturally, we prioritize the separation of concern by clearly defining specific duties among components. We achieved greater modularity, maintainability, and the ability to focus on specific optimization areas. Our design principle emphasizes simplification. This approach aims to streamline complexities, eliminate unnecessary interactions, and bolster overall system resiliency and effectiveness. We also embrace a component breakdown strategy spanning our integration stack. This facilitated targeted layer enhancement, enabling us to address performance concerns systematically. Leveraging indirection at the data source level was pivotal. This mechanism allows us to tackle our performance-related issues, particularly write contention. The creation of a dedicated testing framework was instrumental in our optimizing performance. This framework facilitated repeatable load tests to fine-tune system behavior under varying conditions. We place significant weight on debugging components in isolation. This practice expedited issue identification and resolution, fostering a more efficient troubleshooting process. Using this core principle, we not only solved current problems, but also built a strong, flexible architecture prepared for sustained growth and adaptability. Now I will hand the presentation to Sam, who will explain the solution in more detail. Sam is a key contributor in this project since its beginning. Sam?
Thanks, Hakan. So let's dive in and see what implementing those architectural ideas really means. So one of the initial changes we decided was to create a new service specifically for these bulk calls to implement separation of concern. The now bulk processes will directly communicate with the new data bulk API. This bulk API has endpoints with similar functionality to the original data API, but can be further optimized for bulk operations with specialized operations, memory optimizations, threading changes, and other changes. This also relieves any pressure that the bulk operations might have impacted into the regular OLTP flow to help ensure that our SLAs are still met. The bulk API can also notify changes to the data lake in a different manner that could reduce cost and compute complexity of updates to the data lake. Another way we implemented the architecture was to use indirection. So bulk changes are now quickly upserted into the specialized side data source based on IDs. The side source collection only has an index on the ID, which, combined with ID-based upserts, allows it to be significantly more performant than the main collection. In addition, the side source can be unsharded if you prefer. Now, one drawback this introduces is that reads must be sent to both the data sources, but we can do this in parallel and the results combined in the API service itself. A separate process can be utilized to merge data from the side source back into the main source asynchronously. This can be optimized to scale down during peak loads and scale up during lighter loads. We do this to keep the side source small and manageable. And now presented here is a full picture of the architecture of this solution. You can see how these new changes fit in to increase the performance and reliability of the overall system while still maintaining the OLTP flow. With these components, we can now handle bursts of bulk operations in a timely and performant manner. Now, to make sure that we could test this system correctly and it would meet all of our requirements, we wanted to ensure that the architecture would be verifiably correct, in addition to handling the traffic in a more performant manner. We used monitoring tools and verbose logging to continue to refine our API calls to be as close as possible to just directly calling via a shell. Because we had delineated the layers, we could test each layer individually and quickly iterate on those changes. We also repeatedly ran full system end-to-end tests across all of the layers while we were iterating, so that we could identify and fix any remaining issues. Now I'll pass this back to Anand for our scale and outcomes.
Thank you, Sam. You heard about predictability being one of the key objectives. To achieve predictable outcome, we needed an experimentation tooling infrastructure to set up experiments in rapid succession. We built an experimental toolset to generate the data, run the load test, and a verification API to validate the state change after the load test. Once the tooling was ready, we set up a series of rapid experiments to measure the impact of the changes, essentially the pertinent performance characteristics, such as IOPS usage, read latency, write latency, and replication lag. The experiments helped us determine the bounds of the system, and in particular, the batch size for the bulk request to the data store, degree of parallelism for bulk operations per container, and the number of containers needed. In addition, the IOP threshold for the sweet spot to share the load between the bulk operations and OLTP processes, that was critical for us. The experimentation allowed us to test different layers separately or in combination. Ultimately, we were able to run 2 to 3 experiments with hundreds of millions of bulk operations in each run on a daily basis. We went with high confidence in integrating our API with our upstream and downstream services and without any issues. Now, let's look at the outcomes. We were able to take bulk operations capability to production without any issues and improved upon the already performing numbers of the old system. We have not only survived the data growth over the last 3 to 4 years, but we are well poised to thrive with our new data platform. We handle hundreds of millions of bulk operations on a daily basis, but we are set up to handle 1 billion plus a day as the data grows. We thank you for listening to our presentation and welcome the questions. Please put them in the chat and we'll get back to you after the conference.